and welcome to this technical webinar, Large Turbo Generators Hydrogen Auxiliary Systems 101, presented by E1 Utility Systems and hosted by Energy Tech Magazine. My name is Andrea Hauser, and I'm the Managing Editor for Energy Tech. I'll be your moderator today. Our webinar today will discuss the equipment used to monitor critical parameters of the hydrogen gas auxiliary system used to cool large turbo generators. This will be a refresher for those of you who are more experienced power plant employees and provide new information for those of you just getting started in the field. We're joined by Steve Kilmartin, Director of Products and Markets for E1. The presentation will last approximately 45 minutes and will be followed by a Q&A session. Steve, please begin.
Thank you, Andrea. Before I start, I'd like to read from an article that was published in the April 2008 issue of Energy Tech Magazine. A study by the Department of Labor confirmed that the average age of workers in the energy industry is now over 50 years of age. And the industry estimates that up to half of its current workforce, more than 500,000 workers, will retire within the next 5 to 10 years. That study was conducted 6 years ago. What this means is the energy industry has lost or will be losing a large number from its skilled workforce, and these employees need to be replaced. Everything in this presentation is about safety, efficiency, and risk mitigation. We're going to talk about why hydrogen is used as a cooling gas. We'll talk about the hydrogen cooling system in a generator. We'll talk about monitors and sensors that are used to measure critical parameters in the generator. And we'll talk about training, calibration, testing, and standard operating procedures. This presentation was created for people with little or no experience with hydrogen auxiliary systems. It may serve as a refresher for experienced power plant personnel, as Andrea said. However, I'm hoping it will provide new information for power plant employees entering into this field. For those of you that have sat through my previous webinars, the next couple of slides will be a review. In the late 1930s, there was an increasing demand to get more megawatts out of generators. With generators, more megawatts means more iron. They get physically larger and generate more heat. In order to satisfy the demand for power without increasing the physical size of the generator, a different method of cooling was required other than air. Imagine using a very explosive gas like hydrogen to cool a large machine that has components that are spinning at a very rapid speed. I find it very interesting that someone decided it would be a good idea to cool a generator with hydrogen. However, the idea worked, and now all large generators are cooled with hydrogen or a combination of hydrogen and water. Why hydrogen? Well, hydrogen provides less windage losses or frictional losses. Hydrogen is four times less dense than air, which means you can spin the rotor in a generator with hydrogen a lot easier than you can spin a rotor in an air-cooled generator. Hydrogen has better heat transfer characteristics. It's 14 times more efficient at removing heat than air is. The bottom line is that you will get more megawatts per pound of iron if you're using hydrogen as a cooling gas. From this chart, we can see how hydrogen purity affects windage losses, which has a direct effect on financial losses. You can see if my purity is in the neighborhood of 91%, I've got 1,500 kilowatts in windage loss. However, if I'm operating in the neighborhood of 98, 99%, my windage losses go down close to zero. And this has a direct effect on financial losses, or how much it costs to generate power. There are additional benefits of using hydrogen as a cooling gas. Because the generator is sealed, you're less likely to get contaminants in the generator as you would an air-cooled generator. Because it's a pressurized vessel, it suppresses partial discharge and also increases the level of voltage that is required for a component to break down. Hydrogen is not an oxidizing agent as air is, and pure hydrogen will not support combustion. Also, because bottled hydrogen is typically very dry, the moisture or dew point in the generator will be very low. One of the problems with using hydrogen is you have to keep it in the generator case. And because hydrogen molecules are so small, they are hard to contain. This slide indicates a sectioned view of a hydrogen-cooled generator. The outer shell is what seals the hydrogen in the generator. One area that is most difficult to seal the hydrogen is around the part that rotates, or the rotor. So here at each end of the generator there are seals that will seal the hydrogen in the generator. I'm pointing these out to you here. There's this hydrogen seal on the turbine end of the generator. There's a hydrogen seal on the exciter end of the generator. You will also note on this generator, this particular generator has two fans. There's a fan on this end and a fan on this end, which is used to circulate the hydrogen. These fans will create a high pressure and low pressure in the generator, which we'll discuss later. Some generators don't have fans, but have what are called blowers that will be used to circulate the hydrogen, and they are mounted on the rotor also. As I mentioned, the difficulty with using hydrogen is sealing it inside the case. Here's a sectioned view of a seal, a hydrogen seal. How this operates is that I've got high pressure oil that is fed to the seal, and then the oil will go in the direction of the air because it's at a higher pressure, and it will go in the direction of the hydrogen because it's a higher pressure than the hydrogen. You can see that this pressure, oil pressure, is 95 psig, whereas the hydrogen pressure is 90. So the oil will flow towards the hydrogen, flow towards the air, and that will create a seal around the oil, keeping the hydrogen inside the generator. Here's another section view of the generator, and the reason I put this up here is to show the hydrogen circulation, because we're going to be discussing hydrogen a lot and how it circulates through the generator. But you can see the yellow arrows, and these yellow arrows represent the path of the hydrogen and the cooling. And you can see that the hydrogen is cooling the stator. It flows through the stator windings. It flows through the rotor, under the retaining rings. This device up here is a hydrogen cooler. That's a heat exchanger that removes the heat from the hydrogen. And as I mentioned, some generators have fans, some have blowers. This particular one has a blower, and that's what circulates the hydrogen in this generator as long as the rotor is rotating. And here is a hydrogen seal on this particular generator. Some major components or generator auxiliaries are the seal oil and bearing lubrication system, the excitation system. If it's a generator with a water-cooled stator, there's a stator winding cooling water system. Some people will refer to the instrumentation and monitoring equipment as an auxiliary system. You have protective relays for the generator. And then you have the hydrogen cooling system, and that's what we're going to be discussing in this presentation. Major hydrogen cooling system components are the hydrogen coolers and the service water that feeds the hydrogen coolers, the seals and seal oil system, the rotor fans and blowers, and then the gas supply system, which will consist of hydrogen supply. This could be tanks, or it could be a bulk system, could be a hydrogen generator that generates its own hydrogen. Carbon dioxide. Throughout my presentation, I will be using carbon dioxide as a purge gas, although there are some plants and some OEMs that will use a different gas, such as argon, for a purge gas. Then there's the air supply, and then there's a gas manifold that allows you to degas the generator and control the hydrogen during normal operation of the generator. Some major parameters that need to be monitored in the hydrogen auxiliary system are the hydrogen supply system. We want to know what the pressure is. Some users will want to know what the flow is. You always want to make sure that you got enough hydrogen on supply for your day-to-day operation. The CO2 supply system, again, we want to know what the pressure is. And it's critical to know the volume of your CO2, because you want to make sure that you've got enough CO2 on hand in the event that you have to purge that generator, and not just during normal maintenance, but in an emergency situation. The rotor fan differential pressure needs to be monitored, generator case pressure, gas temperatures. This typically is your hot gas and cold gas temperature, and I won't be discussing other temperatures such as a stator temperature. They may have some end winding temperatures. We'll discuss the cooling water temperatures and flows. In detail, we will discuss gas purity, measuring gas purity, not only hydrogen but the purge gases. We will discuss the hydrogen dew point monitoring and liquid level detectors. Another device that is of importance when it comes to the hydrogen is the differential pressure regulator that maintains a set differential pressure between the seal oil and the hydrogen. This is a typical generator P&ID, the hydrogen system for a generator, and we're going to spend some time on this slide. Up here you can see your supply gases, and again we're using CO2 as our purge gas, hydrogen supply, air supply, and then this manifold is used to feed gas in and out of the generator. These are the connections that go to and from the generator. Notice this spool piece right here. This is used to prevent air and hydrogen being put in the generator at the same time. It will not eliminate it. You need to have proper standard operating procedures so that a mistake isn't made and hydrogen and air are put in the generator at the same time. But this spool piece will certainly help minimize the chances of that happening. So here we have the CO2 supply pressure coming in. There is a pressure relief valve so that it doesn't build up too much pressure. We have a local pressure indicator that tells what our CO2 supply pressure is. We also have a transmitter that's measuring the CO2 pressure. That will feed a signal back to the control room so the control room knows what the CO2 pressure is. And note the calibration ports on these, because this becomes important when you are establishing calibration procedures for your equipment. Being able to calibrate the equipment without having to disconnect components or take the unit offline. Here we have the hydrogen supply pressure. Again, we have a pressure relief valve. We have a local pressure indicator to tell us what the hydrogen supply pressure is. We have, again, a pressure transmitter that is feeding the signal back to the control room. And again, we have the cal ports and the isolation valves so that these can be calibrated. On this particular unit, under normal operating conditions, we have a pressure control valve that will maintain the pressure in this generator at 60 psi. Some plants will choose not to use this, and they'll shut off these isolation valves, and they will manually cap off the pressure, meaning an operator will go down there periodically when they get a pressure indication over here. When that drops below a certain point, they'll come open this valve and feed hydrogen into the generator. We have some pressure relief valves that go to the case so that we don't build up too much pressure in the case. This particular one is set at 65 psi, although we're maintaining a pressure in the case at 60 psi. Over here we've got the case pressure indicators and transmitters here so that we know what the case pressure is. I'll show a slide later on that will show the importance of measuring the case pressure. Again, we have an indicator that will give us a local indication, and we have a transmitter that will feed a signal back into the control room. Again, we have the cal port with the isolation valve so that we can calibrate this unit without taking it offline. Here we have a differential pressure indicator and transmitter. Indicator for local indication, transmitter to go back to the control room. Once again, we have calibration ports so that we can calibrate this unit without taking the unit offline. Now, when the generator fan is turning, when the generator is at full speed, we will have a fan pressure and a fan suction. That will create a flow through our analyzer that measures hydrogen purity. So I've got a fan pressure, hydrogen will enter through here, go through a filter moisture indicator, set the flow through this flow meter, through the analyzer, back to the generator. So as long as the rotor is turning, I have a continuous flow of gas going through my analyzer, and I know what the purity is in that generator. If I am on turning gear and my fan is not turning, I need a way to get a sample to my analyzer. So what we do is we have to change this valve. We have to change this valve to go to vent instead of return to the generator. So now I'm relying on the generator case pressure to push a sample through the analyzer out to vent, and I'm using a small amount of hydrogen to monitor my hydrogen purity. Here we have the calibration ports for the gas analyzer, and these can either be tied in permanently to gas connections, or they could be bring bottles in temporarily to calibrate the piece of equipment. You'll notice also here I got a connection for a portable gas analyzer. Some plants will bring in a portable gas analyzer. Although this online analyzer can be used for purging, some plants like to have two analyzers online, just one to confirm the other one is operating properly. Here's a section view of again of a generator, and I just wanted to show this to point out that I've got the carbon dioxide distribution pipe or header that's located at the bottom of the generator. I have a hydrogen distribution pipe or header at the top of the generator. These two lines here are these right here. So I will bring, when I start a generator, I normally will have air in the generator when I'm coming offline or when I've done some work on the generator. So I need to get that air out of the generator so that I am not mixing hydrogen in air and creating an explosive mixture. So what I do is I bring carbon dioxide into this bottom header. Carbon dioxide being heavier than air will create a blanket and flow up, and the air being lighter than carbon dioxide will come out of this top header. Once I'm satisfied that I've got all of the air out of the case, then I want to, and I've got the case filled with CO2, now I want to put hydrogen in there. So what I'm going to do now is open this line to hydrogen, hydrogen being a lighter gas than CO2, open this line to vent, and that will force, the hydrogen pressure will force the heavier CO2 gas out this line. So that's in a very simplistic description of how a generator is purged. One of the things I would like to point out on this slide, as you can see, I have my analyzer feed and my analyzer return. This is generator fan pressure, generator fan suction. This is where I will take a sample when the generator is spinning, when I have a differential pressure. When I don't have a differential pressure, then I got to rely on case pressure again, take the analyzer, go to vent, and the case pressure will create flow through my analyzer. When I'm purging the generator, I don't want to take a sample here, because if I've got CO2 in the generator, that's all it's going to see is CO2. I need to get a representative sample of what's leaving that generator. So what I do is I tie my analyzer to the vent where the gas is exiting and going to atmosphere. And now that gas coming out, going through my analyzer, that's where now I've got a representative sample of the gas that's coming out of that generator during the purging process. This is a hydrogen control rack. This has all the components that we see in this P&ID. So on this rack, we have the gas manifold for putting the gas in and out of the generator and maintaining hydrogen pressure during normal operation. This is that spool piece that will either allow you to put hydrogen in the generator or air in the generator, but not both. This gauge will measure generator fan differential pressure. This one is measuring the case pressure. This is the purity analyzer. This gauge is monitoring the CO2 pressure, supply pressure. This gauge is monitoring the hydrogen supply pressure. In the back are the transmitters, so you can't see the transmitters on this rack. And here are the inlet, outlet to the generator, and also the gas feeds into the rack. I mentioned that it's critical to know what the generator case pressure is, and this generator capability curve indicates why it's important to know the generator case pressure. As you can see, the higher the pressure, the more megawatts that can be produced. A generator capability curve such as this is supplied with each generator by the OEM. One of the things that was not shown in the slides earlier on that P&ID were temperatures and the water flow. So I'm going to talk a little bit about the hot gas temperature. This is monitored by either an RTD or a thermocouple. The cold gas temperature, again, this is either monitored by an RTD or a thermocouple. Cooling water temperature, the inlet of the cooling water temperature, the outlet temperature of the cooling water, and then the cooling water flow. Here's a simplistic view of what I just spoke about. But here you can see I have the inlet cooling water coming into my hydrogen cooler, and then I monitor the outlet. This will tell me how effectively I am removing heat from the generator. And then I have cold gas. Cold gas is usually is always measured before the or after the gas comes out of the cooler. That would be my cold gas. My hot gas is the hydrogen that's entering the cooler. And then you'll notice down here I got some liquid level detectors. These are monitoring for oil or water that could be in the generator. These are switches. I just wanted to again show the hydrogen cooler that is shown here. This part right here is this. This is the hydrogen cooler. And again, we got the hot gas coming in the cooler, cold gas comes out of the cooler, and then my inlet and outlet water are coming over here. And again, by measuring those, we can tell the effectiveness of this cooler and how well we are removing heat. These are liquid level detectors, as is indicated here on this drawing. There would be one coming from the bushing box, and then there would be a couple of them coming from the bottom of the case. One of these is from case, or two of these from case, one's from the bushing box. This is a reservoir where the liquid will build up. In here is a switch that will switch once you get too much moisture in these or too much water in these. Note that they've got isolation valves on them so that I can, first of all, drain them. But as importantly, I can shut these down. Over here is a port that I can put liquid into the reservoir to actually test these to make sure that these are working properly. Now I'm going to spend some time talking about gas purity, not just hydrogen purity, but gas purity in general. Why do we want to monitor the hydrogen purity? Two reasons. One is safety. When hydrogen is mixed with air, it becomes very explosive. It has a very large explosive range, 4 to 75% when mixed with air. We also want to monitor it because of the efficiency, as I indicated in that graph earlier. The purer the hydrogen, the less windage loss there is in the generator, the more effective the generator, the more efficient the generator is, the more megawatts that you can produce. We also want to measure gas purity during the degassing and gassing of the generator. We want to make sure that we get all the air out of the unit before we put CO2 and hydrogen in there. We want to make sure that we get all of the hydrogen out before we put air in the generator. And as we said here, we want to measure the hydrogen purity during normal operation of the generator. These are some methods of monitoring gas purity. A manometer, which it was used, I'll use the term in the olden days. It was a glass U-shaped tube filled with mercury. And what this did is it measured a differential pressure. It measured the high pressure, the low pressure. And the OEM, the generator manufacturer, supplied a graph with the generator. And you could take this differential pressure and convert it into purity. Then later there came a device, a gas density blower, which also measures differential pressure. And again, we take that differential pressure and convert it into gas purity. The most frequently used technologies are thermal conductivity analyzers. There are different types of thermal conductivity analyzers. The one thing they have in common is that they all use a thermistor as a sensing device. However, the type of thermistor and the electronics that are used can vary greatly from analyzer to analyzer. There is a vibrating element analyzer. This is a newer technology. It is important that your analyzer is a triple range analyzer that can determine not only hydrogen and air during normal operation, but also hydrogen and CO2 and air and CO2 during the gassing and degassing process of the generator. It is also very important that these devices, since they are analyzing hydrogen, be rated to be used in a hazardous area. This is a picture of that portable analyzer that I mentioned earlier, and that some power plants like to use these to provide a redundant signal during the purging process. This analyzer is not rated to be used in a hazardous area, so it should be used in a well-ventilated, safe area. Here, I just wanted to point out the portable gas connection again, and you'll note that the portable gas analyzer is on the same line as that the permanently installed analyzer is. Now I'm going to talk a little bit about monitoring dew point. Why do we monitor dew point? In my opinion, and this author's opinion, is that the most important reason is component and insulation failure. You want to keep your dew point low so that you do not create situations in the generator where components will fail. A secondary reason is efficiency. However, I will state that it takes a large amount of dew point in a generator to affect the efficiency of the generator. Some other points about dew point. Let me back up. Increased dew point can support insulation failure, electrical tracking. Usually this takes place in the rotor, on the rotor windings. Also, a higher dew point has a corrosive effect on some generator components. The retaining rings, which are the most highly stressed mechanical component in the generator, it's very important that you maintain the integrity of the metals, the retaining rings. And there are certain metals that become affected by having a higher dew point in the generator to a point where they can break down. Now, cycling a generator will not cause dew point to go up. However, if I'm cycling a generator, what I'm doing is I'm heating and cooling the generator. And what will happen on a base load unit, for instance, where the unit may be warm all the time, you're less likely to have condensation form. But on a cycling unit where you're bringing a generator down and it's sitting for a while, there is a possibility where you could have condensation form in the generator. Some other points about dew point. What is a good dew point? Most manufacturers will say 0 degrees C. You want to keep your dew point lower than 0 degrees C. 0 degrees C normally being an alarm point. Hydrogen from bottles or bulk systems usually is very dry, and the hydrogen from a hydrogen generator system is always dry. So where does the moisture come from? In most cases, the moisture in the generator will come out of the seal oil. However, it could come from the cooling water, whether that's from the coolers, a leak in the coolers, or a leak in the stator winding, if it's a water-cooled stator. With baseload generators, as I said, you have a constant warm temperature in there. However, with peaking units that are cycling, you have a chance for the temperature to fluctuate, and you also have a chance for condensation to form inside the generator. This generator, this picture is of a retaining ring failure. As I said, the retaining ring is the most highly stressed component in the generator, spinning at some cases 3,600 RPMs, on a nuclear unit 1,800, or if you're in Europe, 3,000 and 1,500. But these units, these retaining rings, older ones, it was very important. Older rings that were made of 18.5 stainless steel. It was very important to keep the hydrogen dry because moisture affected 18.5 stainless steel retaining rings, causing the integrity of them to go down so that they would actually fail. And in this picture, this is something you certainly don't want to happen. This is a picture of the end turns on a rotor with the retaining ring removed. And this is an example of an insulation failure on these turns. Moisture, along with other contaminants, can form a conductive bridge that can lead to electrical tracking or cause insulation to deteriorate and cause a coil-to-coil short. There's a great paper that is written by the late Don Albright, founder of Generator Tech, that discusses insulation failure in detail. How do we monitor dew point? Well, here's a list of some sensors that can be used to monitor dew point. Ceramic sensor, silicon-based sensor, aluminum oxide. I don't believe that chilled mirrors have ever been used in hydrogen-cooled generators, but chilled mirrors are used to monitor dew point. All of these devices are measuring a change in an electrical property, whether that be capacitance, resistance, or impedance. Again, what is the source of moisture in the generator? Well, in my opinion, the primary source is seal oil. On some generators, the oil that's used for the bearings in the seal is the same oil that's used in the bearings in the steam turbines. And they will pick up moisture on the steam turbines and then carry that moisture to the generator oil, the seal oil, and the bearing oil. If the vacuum system on these units is not operating properly, then the hydrogen will actually absorb the moisture and pull the moisture out of the oil. Hydrogen coolers can be a source of the moisture. Stator water cooling systems can be a source of the moisture. Years ago, there was a manufacturer multiple manufacturers that had clip problems, and this is where the water transferred into the winding, and these clips would leak, and they could add moisture to the hydrogen. And then the importance of thermal cycling of a generator. Again, this will not create moisture, but it can create condensation to form on components inside the generator. Now we're going to spend a little bit of time talking about training, calibrating, and testing. You need to have good documentation. As I mentioned earlier, we've got a young workforce that's entering into this field, and it's very important that you have good documentation. In the past, power plants had good apprentice programs that would train young employees, or they had younger workers, younger employees working with more experienced employees for several years before they were, let's say, on their own. However, that's not taking place anymore. With the reduction of the workforce, this is no longer the case. So since you've got young, I'll use the term inexperienced workers coming into the power plant, it becomes more important that you have well-documented procedures. You should have well-written test procedures for all the instrumentation. If you don't, talk to other plants. See if you've got a sister plant. See if they've got the documentation. Talk to plants that aren't part of your system. I've found in this business that people are more than willing to share information. Also, you can talk about the instrumentation provider. They may have test procedures for the instrumentation. You should have well-documented training programs. Again, if you don't, talk to other plants, see what they're doing. Also talk to the manufacturers of the equipment. A lot of times they offer training programs and will come into your plant to either demo the equipment or to provide training on that equipment. Make sure you have reliable and accurate calibration and test equipment. And make sure that that test equipment that you're using to test your pressure gauges and your differential gauges and your purity analyzers, make sure that it is calibrated and within specification. You may have to send that back to the factory in order to get it calibrated and certified. Maintain a calibration schedule. Know how often the equipment needs to be recalibrated or tested. I'll give you an example with dew point sensors. Dew point sensors need to be recalibrated every year. And they cannot be done in a power plant. They need to be sent back to the manufacturer in order to be recalibrated. And the problem with them is they could give you a negative low reading. So it's important to know that although these sensors may look like they're giving you a good reading, they could be out of calibration. So you need to know or have a calibration schedule. Make sure you have the proper tools. Remember that there may be times when you are working in a hazardous area, and you should have equipment and tools that are suitable to be used in that hazardous area, such as non-sparking wrenches, for an example. To sum up this slide, it's critical to have well-written, up-to-date, standard procedures, testing, training, and standard operating procedures. In closing, we know that hydrogen is a very effective cooling gas. By using hydrogen as a cooling medium, we can get more megawatts without increasing the size of the generator. Again, as I mentioned earlier, more megawatts per pound of iron by using hydrogen as a cooling gas. We discussed the hydrogen auxiliary system and the importance of monitoring certain critical parameters. We discussed the need for well-written test procedures, training programs, calibration schedules, and standard operating procedures, and the need for proper tools and test and calibration equipment. As I said at the beginning of this presentation, and I'll end the presentation by stating, this is all about safety, increased efficiency, and risk mitigation. Thank you.
Okay, and now we have quite a few questions, Steve. So our first one is from Paul, and he's asking, how often should the hydrogen and CO2 safety valves be tested or replaced?
They're difficult to test. I certainly would recommend at the end of every outage that they be calibrated and tested. The problem with them is that you can't take them offline in order to test them. So at a minimum, they should be tested during every outage. And I would only recommend replacing them if they fail test.
Okay. And then we have a question from Andrew, and he's wondering, what are acceptable inlet to the generator and outlet from the generator hydrogen dew point temperatures?
Going into the generator, coming from a bottle or tank or bulk system or coming from a hydrogen generator, typically the hydrogen dew point will be less than 40 degrees C. And I would, if I had to put a limit on it, I would say it should be a minimum of negative 20 degrees C. However, my experience indicates that it's in the neighborhood of 40 degrees C when it's coming out of a good bottle or a good tank farm. It is possible to get a bad bottle and and have high moisture content in there, but typically it's pretty dry. Now, as I also mentioned earlier, if you have a hydrogen generator that's producing the hydrogen, they produce a very low dew point, and I suspect, or I recall that they're in the neighborhood of -40 degrees also.
Okay. Then we have a couple questions about pressure and efficiency. We have a question from Ken about what is the typical efficiency loss if the H2 design pressure drops?
That's a very good question, and I don't think I can answer it. The reason being is that it will vary from generator to generator, and that's a question that would have to be answered by the generator manufacturer or the OEM.
Okay. And then we have a question from Alex who's wondering, what is the pressure of the H2Vs, the seal oil, which one is higher than the other and why?
The seal oil is always higher pressure than the hydrogen because you want the seal oil to flow in the direction of the hydrogen.
Okay. And then from Bonnie, he's wondering, what is the recommended pressure of water in the hydrogen cooler, more than or less than the hydrogen pressure inside the generator?
I believe that it's always lower because you want the hydrogen to flow. You would prefer to have the hydrogen flow into the water versus having water flow into the generator. So the cooling water, I believe, is always lower than the hydrogen pressure.
Okay. And then we have another question from Mark, and he's wondering, what effect does higher hydrogen temperature have on generator efficiency? Is there an industry-accepted upper limit for this temperature, or is it a manufacturer-based limit?
When we're discussing temperatures, it's important to know: are we talking about, for instance, are we talking about the core temperature? Are we talking about a stator winding temperature? Are we talking about the cold gas, hot gas temperature? Again, it gets back to the manufacturer, and the manufacturer will have a recommendation on what is an upper limit for my hot gas temperature, and when should I be concerned about this. Where this becomes very important is in southern states or in warmer climates where your cooling water temperature will elevate during the warmer months so that you're now less effective in removing the heat from the hydrogen. But to answer what the limit is, again, that is generator specific, and you would have to check with your OEM on that.
Okay. And then we have a lot of questions here. Steve, I think you're going to have some follow-up emails too. Our next one is from Ken, and he's wondering, how do you address low H2 purity?
Depending on the seal oil system of the generator, and I'll discuss both of them. There is a manufacturer out there that makes what is called a scavenging type seal oil system, or what is referred to as a bleed and feed type seal oil system. And the way that this works is that they're bleeding hydrogen through the seal oil system in order to maintain hydrogen purity. The OEM has a recommended set point for those bleed rates, and typically it's in the neighborhood of 1,500 cc's per minute out of each end of the generator to maintain a specific hydrogen purity within the case. Now, on some of those generators, if the purity is not where it should be, then that scavenging rate or that bleed rate can be increased, and then that will increase the purity inside of the generator because you're feeding more pure hydrogen into the generator. On a vacuum treated seal oil system, the only way to, if your purity is dropping in that type of a system, first of all, you want to know why that hydrogen purity is dropping, because you may have either a major leak or your seals may not be operating properly. But the only way that you can increase the purity of a gas in a vacuum treated system is that similar to the scavenging seal oil system is you got to bleed hydrogen. You got to bleed off hydrogen and put fresh hydrogen into the case.
Okay. And then we have another question from Paul, and he's wondering, should a hydrogen dryer be operated when the generator is offline for a few days?
Yes. Yes, it should. And it's very important that the dryer that you are using has a mechanism that will circulate the hydrogen in the generator. As I mentioned in my presentation, when generators cool down, there's more likelihood for condensation to form on components in the generator. So it becomes very critical that you're drying that hydrogen when you're on turning gear versus when you're at full load. So you want to make sure that your dryer has a way of circulating that hydrogen not only during normal operation when the rotor is spinning, but also when you're on turning gear, so that you can circulate that. Some dryers are connected so that they're relying on the fan differential pressure to circulate hydrogen through the dryer. And this is fine during normal operation. But when you go down on turning gear or when you come offline, you want to continue to dry that hydrogen, so you need to wait a method of circulating that hydrogen while you're on turning gear. So yes, it is very important that you dry your hydrogen when you're either offline or on turning gear.
Okay. And then Chris is wondering, what method of pressure control is best? Automatic addition or manual addition? And what are the pros and cons?
That depends on the plant, and it depends a lot on operators also. There are operators that can tell you when they change a bottle of hydrogen out. So they know that, if they change one bottle every 24 hours, they know they're using 300 cubic foot or 500 cubic foot of hydrogen. That's what my leakage rate is per day. When you go to an automated system, you still have to change the tanks out, but there are operators, there are plants that prefer to manually top it off. There are plants that will use the regulating control valve to maintain the pressure in the generator. Then there are some plants that will put in transmitters, flow transmitters, mass flow transmitters, so that they can monitor the hydrogen usage also, so that they're not only topping it off automatically, but they're also monitoring that gas flow at the same time. And I think some of the, and again I'll use the term old timers, that would prefer to manually top that off, as long as they had a mass flow meter in line so that they knew what their hydrogen usage is, that may be okay with them.
Okay. And then we have a question from Tom, and he's wondering, is the water source for the hydrogen cooler typically from an open cooling tower or from a cleaner closed-loop water cooler?
I mean, I'm aware of some that come from a river. To be honest, Andrea, I'm not certain about that, but I suspect it could be both.
Okay. Okay.
If some of these people have questions that I can't answer, they can see my email on the screen right now, and if they send me an email, I can certainly find out the answer to those questions, unless it's OEM specific where they have to go to the generator manufacturer.
Okay, okay. And then we have a question from Thomas. We have about 5 more minutes for questions. We have a question from Thomas. What are typical limits for hydrogen leakages in a water-cooled generator?
I have witnessed or know of generators, and EPRI did a study of this once where they sent out questionnaires to some of their customers, and what I can tell you is that a tight generator is in the neighborhood of 500 cubic feet per day. Some generators, the acceptable usage is in the neighborhood of 1,000 cubic feet per day. When they get into the neighborhood of 1,500 cubic feet per day, almost everyone will consider that high usage, and they'll need to look to determine where I'm losing my hydrogen, where's my hydrogen going. But again, this is generator specific, manufacturer specific. If someone were to ask, I would say it should be in the neighborhood of 1,000 cubic feet per day, and I would not want to be using anything more than that. If you're using more than that, you should start looking at where this hydrogen is going.
Okay. And then we have a question from Lawrence, and he's wondering, between the H2 bulk supply system and the generator is typically a high flow shutoff valve. Could you please provide examples of valves in use in the industry?
I can. I'm not sure if they're looking for a specific model number and manufacturer, but we have supplied these, and again, if he sent me an email, I can give him a specific valve that we have used as a shutoff valve in those lines.
Okay. And then we have a question from Jasvir. What is the best method of dew point measurement, continuous online or periodically? If periodically, then what is the best interval?
I would recommend continuous dew point monitoring, as I would purity monitoring. Now, dew point usually does not change rapidly in the generator, so periodic sampling is acceptable if you have a good program that, and let's say we do it on a weekly basis, and we have good reliable equipment that we're periodically taking a sample. One of the reasons that I recommend a continuous monitor is because it's always there, and usually someone will always be monitoring that, or it will send a signal back into the control room so that the operators always know what the dew point is, versus taking a sample and putting it in a log someplace. So my personal recommendation would be a continuous online monitor.
Okay. And then we'll take our last question from Dick, and he's wondering, what is a typical volumetric flow rate of H2 through the generator?
I think that's a similar question as to what we answered on the regarding the usage being 500 cc's, 500 cubic feet per day being a tight unit, 1,000 being maybe a limit where you want to start to be concerned about it. But that's typical of the flow rate through a generator, a daily flow rate through a generator. Again, if they're looking for the volume of the generator, how much hydrogen is in the generator, again, that's an OEM specific question, and that will vary from generator to generator.
Okay, are you up for one more question, Steve?
Yeah, go ahead.
Okay. We had a question about the purity on slide 2, the purity versus windage losses.
Yes.
And they were wondering if you could explain that.
What that graph indicates is that as my purity drops, and by the way, this was a graph that was created by an OEM, that was a generator manufacturer, but what that indicates is that as my purity drops, my windage losses, which is on the right-hand side. By the way, again, they can send me an email and I can send them that graph. That was I'll call it a general graph. It certainly was not generator specific, but what it was indicating is that as my purity drops, my windage losses are going up. And the reason my windage losses are going up, obviously, is because I've got air coming in the generator, and that's a more dense gas causing the windage loss to go up.
All right. And with that, we're going to going to conclude today's webinar, Large Turbo Generators, Hydrogen Auxiliary Systems 101, with Steve Kilmartin from E1 Utility Systems. If you have any other questions, please feel free to email Steve at the address shown. A recording of this webinar also will be available to download at energytech.com by Friday, October 17th if you would like to watch it again or share it with colleagues. Thank you, Steve.